And who should walk by but the Vint Cerf? The reason why we say surf the internet, that guy is walking through the cafeteria with a tray. And Kristen, ever being the opportunist, walks up to him and says, Vint, I know you're busy. If there's any chance you have in your busy day to stop by, I've got these amazing educators. If you have any thoughts you'd like to share with them, that would be fantastic. And he, being a gracious gentleman that he is, he said yes, stopped in, and blew us away with 25 extemporaneous minutes. And it was a highlight for me of an already amazing day. So from that relationship, we reached out to Vint, and he was gracious enough to be our keynote speaker at CUE's 30th anniversary conference in 2008. And when we did this, we thought, who better to kick it off than inviting Vint Cerf back? So one last story about Vint, and then I'll introduce and bring him up on the stage. So we took him to dinner that night when he was our keynote. And it was one of those restaurants that has kind of crepe paper as the tablecloth that you could write on. And he started telling the story of the creation of the internet, the first 4 nodes, when it was ARPANET and DARPANET. And he starts drawing, just sort of impulsively, just takes out a pen and starts drawing. Do you remember this? And so I have it, of course. There were about 3 or 4 of us that as soon as we got up to leave that dinner, we all dove for this right here. I came up with it somehow. I don't exactly know how, but I think Brian Bridges and I think Steve Glyer was there, and Marisol, that all of them said that I could have it. So that is framed because it was a Father's Day present last year to actually frame it. So I brought it because I neglected to ask if Vint would sign it, so we'll see. I don't know. A little later tonight, maybe I can ply him with some wine and he might actually sign it, and then I can try and convince people that this is actually from, early, mid-20th century when they were planning it. And Vint Cerf signed the original plan. We'll see how that works out on eBay. In any case, ladies and gentlemen, one of the fathers of the internet, the gentleman that helped with TCP/IP and actually took the blame for IPv4, but helped us solve that with IPv6. So thank you, ladies and gentlemen, Vint Cerf.
Well, hello, everybody. Thanks so much for letting me take some of your time this afternoon. I'm really excited about the relationship between Google and CUE. And I have to say that I have other hats as well that make me very pleased to be part of your community. I'm also currently serving as president of the Association for Computing Machinery. And one of the things that we would like very much to see happen is that computer science becomes a part of the normal STEM curriculum, and I'm going to talk a bit about that. I am not going to talk about, and I can find to tell me what I'm not talking about. Where is it? It says I am not talking about applications that you would normally use in order to entice students into an interest in science and technology. And so what I'm going to talk about that is that there are lots and lots of people who are already hard at work, you included, creating a lot of applications that teachers can use and kids can use to take advantage of the internet as a platform. So whether Earth and the layers on top of it, or Google Maps, or other kinds of applications, it's a wonderful and rich environment in which to engage kids in using the net and its technologies for exploring science and technology. But I don't want to spend a lot of time talking about that because others will do that, and I have a specific message I want to deliver with regard to programming. At ACM, we have been, together with Google and others, trying very hard to get 10,000 teachers trained across the United States to be fully equipped to teach kids about computer science, how computers work, what programming is about, and so on. It's not that we want to turn them into programmers, but you'll see what the motivation is. The second thing I wanted to mention is I have another relationship with an organization called Gallup. They're the people that you know of as doing polls all around the world. Well, they do more now. They are consultants to corporations to help them figure out how to best use their employees, and as well as trying to understand the economics of global commerce. But one of the things that they do is called Strength Finder. And the thing which I believe you should resonate with is that the Strength Finder idea says, let's help people find out what they're good at, and then let's encourage them to keep going along that direction. Too often you hear about programs that tell people you're not very good at this, so you should concentrate on fixing what you're not good at. I'd much rather have kids discover what they're really good at and encourage them to go further with it. And the Strength Finder is an example of a tool that helps you do that. So let's jump into a little picture here. This takes you back to the 25th anniversary of the ARPANET. And the ARPANET first emerged in 1969. The first node was at UCLA. And these three guys that you see in the picture here, John Postel on the left, Steve Crocker in the middle, and me on the right, were graduate students at the time. And we ended up being responsible for doing the design of the communication protocols for the computers that were on this ARPANET packet switching system. The thing that was so exciting about it is that we thought that the principal investigators, the professors, would be telling us what to do, and they basically said, go figure it out. So as graduate students, we had the opportunity to literally pioneer some of the designs of protocols for computer-to-computer communication on this ARPANET project. This is the predecessor to the Internet. John Postel went on to become the Internet Assigned Numbers Authority. And if any of you happen to be following Internet governance debates that are going on today, you may know that John Postel served for well over 25 years in this capacity, managing the top-level domain space, the Internet address allocations, and curating the protocol parameters needed to make the Internet protocols work. Unfortunately, John passed away in 1998, just as the Internet Corporation for Assigned Names and Numbers was being set up to undertake to manage those specific parts of the Internet architecture. The guy in the middle, Steve Crocker, is now the chairman of ICANN, and I'm the former chairman. So what you see here is an exciting celebration of the 25th anniversary of the ARPANET with three guys that got lucky because we were in the right place at the right time. Could not have planned this. It was just good happenstance. This is what the Internet looks like on the inside. And the reason I show you this picture is not only to give you the impression that it's really big and sprawling, which it is, but each of these different colors are different networks that make up this network of networks. What's interesting about this is that it is not a hierarchical system. This is a fully distributed environment. Nobody is absolutely in charge. ICANN has the responsibility of allocating addresses to make sure that two different networks don't get the same address space, because that would cause a lot of confusion in the routing algorithm. This is a gigantic collaboration. These entities that run pieces of the Internet could be for-profit, not-for-profit, government, or private sector. And they decide what software to run, what hardware to buy, and who to connect to. There is no top-down dictation of any of that. And the reason it works is that there are a set of protocols that everybody adopts as standards, and the standards assure interoperability. And that has created a remarkable environment for creativity, and that's one of the reasons that I want kids to know about software, because if anything, the Internet is this fabulous resource for allowing people to explore what you can do with software. So I think kids should learn computing. It's not that I want to turn them into programmers, but I want them to learn the discipline that you need in order to program. You have to understand problems. You have to figure out how to decompose them into pieces. You have to figure out how to compose them back together again in order to make the computer do something that you're trying to get it to do. You want them to learn the notion of generalization. So you might have a specific problem you have them concentrating on to write a program to accomplish, but what you want them to be thinking in the background, what if I like that? But not exactly the same thing. How do I create a software environment that could be used and adapted to solve other problems? And this generalization is a really powerful tool and something which we benefit from every day. It also forces you into writing things down to say, what is it that you're trying to accomplish? How is it that you're going to accomplish that? How do the pieces interact with each other? What interfaces do you have to identify, especially if more than one person is involved in the project and you have to get people to cooperate, you have to get their software to cooperate. That's systems design. And I can tell you we don't have enough systems level thinking in our environment. This applies not just to software, but it applies to all complex systems, including the global economy. Getting people to think about that's really important. And then, of course, they actually have to do something, which is the other thing that got me attracted to computing. You get to create this little universe and you're in charge of it. You create this piece of software and it does what you tell it to do. Actually, it does exactly what you tell it to do, not what you want it to do. And when the two are not the same, that means you have a bug. And that's another hard thing to learn, is how to find the bug. That's another discipline that's really important. Then there's the question of, does it do what I want it to do? And how do I know? How do I test that? How do I check for the most extreme cases of input and output? You know, people type things wrong. Is my program prepared for somebody giving you bad input, for example, so that it doesn't fall over and die? This is an example of learning how to write software in a robust environment. And once again, the generalization of that is designing systems that are prepared to deal with unexpected cases, or cases that, you know, low probability, but when they happen, they cause a lot of trouble. There's another notion of model checking, which has become quite a popular element in computer science. Model checking basically says, I've got this piece of software, and it's trying to accomplish something. I'd like to be able to say something about the software's state as it's going through a computation. If I can actually make an assertion about the state of the software or the state of the program at various stages in the computation, and then say something in the sense of proving that that assertion is going to be correct for that program at that point, this is an incredibly powerful way of trying to make sure that a piece of software will only do what it's supposed to do and not something else. Then comes simulation and emulation in virtual machines. Now, this is a big deal, especially if you are in a cloud-like environment. The machines that are in the clouds, Google's and others, are now capable of emulating other computers. What's important about that is that you can actually reach back in time, if you want, run old programs on emulated machines in this cloud. So this is a really powerful way of letting kids see what was life like 30 or 40 years ago. People have got Pong is running again in these environments. Now, I know some of you will remember Pong. It's probably the dumbest game imaginable, you know, boing, boing, boing. And we would sit there for hours going boing, boing. And the kids today look at this and they think, boy, you know, bunch of kooks. But in fact, it's kind of interesting to be able to recreate the past and let people see what it looked like. But this also turns out to be important for preserving things for the future. If you really are concerned about preserving digital content, whether it's a program or you know, video or audio or a game or something else, or text or some other object, digital object, a spreadsheet, for instance, if you're interested in preserving this over long periods of time, I'm talking hundreds of years, then this notion of emulation in virtual machines turned out to be incredibly important, because you may have to recreate the machine, the operating system, and the application that processed a particular digital object that you're trying to hang on to. This is a non-trivial exercise and something I'm personally very interested in. My model for this is that suppose it's the year 3000 and you've just done a Google search and you've turned up a 1997 PowerPoint file. Now let's imagine you're running Windows 3000, just for the sake of argument. The question is, does Windows 3000 know how to interpret a 1997 PowerPoint file? And the answer is probably no, and this is not a gratuitous dig at Microsoft. Having a piece of software that can correctly interpret a 1,000-year-old data object is actually pretty hard. Even if you're talking open source, it's not hard, it's not easy. So this notion of being able to preserve digital content using some of these concepts of emulation and the like is really important. The other thing that I would draw to your attention is the increasing availability of tools and devices that you can use that let kids explore what's possible. So Raspberry Pi, a little very inexpensive processor, or Android, the operating system, or Google Glass. Let me pause. On Google Glass, just by way of example, this is the most amazing opportunity to bring computing into your normal human discourse environment. So that the Google Glass sees what you see and it hears what you hear, so it has some context. It might even know where you are if it has a GPS receiver or uses the GPS receiver on your mobile. So the idea is that we can bring software to bear to be aware of what's going on in your environment, and that means you can call on it, not just as a tool, but call on it as almost as a colleague to help you. I'll give you some examples of applications that might drive some interesting thoughts. Mindstorm coming from Legos, CubeSats, another very interesting small size satellites that kids could actually write software for, and we could launch them fairly inexpensively. I mean, I can't imagine anything more exciting than having your software in orbit doing something. I mean, it's the ultimate turn on. And then robots are starting to become widely available as well. Of course, the idea of getting something to do something autonomously is pretty exciting. And then there's all this various high-level languages like Java and Ruby on Rails, Python, Squeak, JavaScript, and the like. So have just an enormous mass of tools available to bring kids into this environment and learn the disciplines that they can apply in the rest of their lives to other things than just software designing. Now, this is, you know that that Dr. Seuss not only did paintings, but he did sculptures. And I found this one in a little store in San Francisco a few years ago, and I couldn't resist the tagline here. Now, you all know about MOOCs. We're very excited about MOOCs at Google. In fact, one of our guys was so excited about MOOCs, he went off to start Udacity. Stanford University got very excited about them as well. And the promise of these things is the potential of bringing content to people anywhere in the world where they can get reasonable access to the internet, which, by the way, is another motivation for getting more internet out there. It's one of the reasons that Google has spent so much time and energy on gigabit networks in Kansas City and Austin, Texas, and so on. Now actually 37 cities altogether are part of the plan. So the idea here is to make content widely available. Now, I remember meeting with John Hennessy, the president of Stanford University, who was literally hopping up and down, excited about MOOCs. And I said, John, why are you excited about MOOCs? You guys charge whatever it is, $50,000 a year to get a 4-year degree. You know, a MOOC is very different. And he says, you didn't do the math. He says, what do you mean I didn't do the math? And he says, okay, let's walk through this. Let's suppose that you have 100,000 people taking a class, and they each are charged $10 for the class. That's a $1 million class. I don't know how many professors have ever taught a $1 million class. Now, you hear these other things like, oh, well, there was the first class that my colleagues taught that 160,000 people signed up for. It was an artificial intelligence course. And of the 160,000 people that signed up for the class, only 23,000 passed the class. And I heard some educator, saying, well, that really is crappy. It's clear that was a waste of time. It's a lousy way of teaching. Only 23,000 managed to pass the course. And I remember thinking, let me see, how many students have taken that class, and how many, Mr. Computer Science Professor, how many have you taught in your 30-year history of teaching? And the answer is probably not 23,000 people. So although it's true that not everybody passed the class, what's interesting is an awful lot of them stuck with it enough that they got some use out of it. They just didn't either stay with the whole course and finish it, or had maybe only partially able to pass the exams, but they still got some exposure. So I'm a big fan of MOOCs for economic reasons as well as for reach. You can do a lot with $1 million. I mean, you can pay for teaching assistants who will service small groups of people. You can imagine exporting that task to wherever a group of kids happens to be who would like to have some hands-on attention. So it's a really attractive possibility. Now, it turns out it's not so easy, and to drop down to the bottom here, Dave Patterson is a former president of ACM, has done a number of MOOCs, and he said in a meeting I was at recently, it's harder than it looks. I mean, doing a really good job on this kind of teaching capability is not easy. For one thing, figuring out what are you going to teach, how do you whack it up into small enough portions so that people can absorb and then get tested on how well they've learned that part. Then you have to figure out what to do if they don't pass this little test. And you need to create the remediation material so that if they got the wrong answer, you zip them off to another 5-minute or 10-minute remedial thing. And you have to figure out what to say. You have to figure out what model in their heads caused them to get the wrong answer and how do I fix that. So that's not easy. Then there's the problem of scale. You can do multiple choice. That's pretty easy to do automatically. But if you have other kinds of things where you want to grade somebody's writing skills, or you want to grade a computation and see their work, that's harder. And figuring out how to do that at scale is a non-trivial exercise. So figuring out how to do this in a way that really gives the kids hands-on capability is a big deal. I've already talked about the economics. So although I'm just as excited, I think, as John Hennessy and others are about MOOCs, I think we should recognize that this is not magic pixie dust. This is another example of hard work, persistence, and patience producing good results. Now, programming languages turn out to be really interesting. I mean, they are like natural languages in many ways. They are more rigid. In fact, they have this interesting characteristic that they force you to find a way to express what it is you want to do within the confines of the language itself, within the semantics of the language. So there's a lot of material. I mean, if you go to Google Scholar or just generally go to the digital library at ACM, you'll find a whole lot of material about proofs and programming languages. This has been going on for years. People have always wanted to be able to prove that the program does what it's supposed to do and nothing else. And of course, this is a really difficult thing. It's hard to prove that it doesn't do something. You can say something about what it does do, but it's a little hard to prove that it doesn't do something that you don't want it to do. So this is a non-trivial exercise. But if you start thinking about writing programs with the idea in mind that you're going to say things, the assertions about how the program is behaving, that you can demonstrate there's a logical, a sequence of logical steps that persuade you that the program is confining its behavior to what you want it to do. This is a pretty powerful way of learning how to write software that's robust and reliable. So I do think, though, as my little last bullet says, that there is no programming language that can keep programmers from screwing up. But it might make it harder to screw up, and that's a good thing, especially considering that you and I are increasingly dependent on an absolute sea of software. All the devices that are part of the Internet of Things, which we'll talk about momentarily, are surrounding us, and if that software doesn't work right, it has pretty direct impacts on all of us. Here's something, if you are in the business of trying to teach kids programming, I strongly urge you to go track down Bret Victor's YouTube videos. The guy is absolutely wonderful. He's refreshing, he's enthusiastic, and he talks about feedback loops. When you're writing software, sometimes if you're not in the right environment, you can't tell what your software is going to do till you run it. And what Bret says is that you should be running the software while you're writing it, and it should be showing you what it's going to do while you're partway through the program, and it should show you what happens when you change various parameters or change a piece of code. And so it's like playing a musical instrument from his point of view. Imagine for a moment what it would be like if you played, let's say, the cello, and you wouldn't hear the notes that you played for 30 seconds. Can you imagine what that would be like? Well, it doesn't work very well. He says that for programming, at least certain kinds of programming that has visible output, for instance, or audible output, that immediate feedback is a huge help in figuring out what did I just do to the program, as opposed to having to run it after the fact, after compiling it and everything else. So I strongly urge you to look up Bret Victor. So I mentioned that we were going to talk about the Internet of Things. This is a big opportunity because an increasing number of devices around the house, at home, in the car, in the office, and on our persons are going to be programmable, and they'll be networked. And so this is yet another great, vast kettle of material that you can use to draw kids in thinking about software and programming and systems. Now, there are a lot of devices that I never anticipated would be on the net. We used to tell jokes about ToasterNet. We used to say, someday the toaster will be on the net, and you can, send an SMTP or a control packet to say how burned you wanted your toast. And we thought, ha ha ha, until somebody actually did put a toaster up on the internet and sent packets to it to say how burned you wanted your toast. But refrigerators are now, high-end refrigerators are on the net. I used to wonder, what could you do with an internet-enabled refrigerator? And, obviously you can replace or augment the family communication system. A lot of us use paper and magnets on the front of the refrigerator for family communication. So now you can add blogs and web pages and email and so on, tweets. And I thought, if you could put if everything that you put in the refrigerator had an RFID chip on it, then the refrigerator would know what it has inside. So while you're at work or at school, it could be surfing the net looking for recipes that it knows it can make with what it has inside. So when you come home, you see a list of recipes up on the display. And of course, you can extrapolate this. You might be on vacation and you get an email and it's from the refrigerator. It says that the milk is going to crawl out on its own because it's been in there for 3 weeks. Or maybe you get an SMS on your mobile saying, don't forget the marinara sauce. I've got everything else I have for spaghetti dinner tonight. The Japanese have messed the whole thing up with an internet-enabled bathroom scale. And it figures out which family member you are when you step on the scale, and it sends that information to the doctor, and it becomes part of your medical record, which seems okay until you realize that the refrigerator is on the same network as the bathroom scale. And you come home and you see diet recipes on the display, or maybe it just refuses to open because it knows you're on a diet. So you have picture frames that are cycling through pictures that it has uploaded from a website. We have digital cameras, all of us now, and so we upload our pictures to a common website, and our picture frames around the family download them. And so, if you're grandparents, you can watch the grandchildren growing up, or the nieces and the nephews, and so on. Of course, security is an issue here, because if the website that the picture is downloading from gets penetrated by a hacker, the grandparents may see pictures of what they hope is not the grandchildren. So security turns out to be just as important at home as it is at work. Everybody has a mobile, so you have that. And here's Google Glass in the lower right here. That's Sergey Brin. Here's a scenario that we can actually almost do. And this is the kind of scenario I want kids to grasp and feel challenged to try to pursue. Imagine we have a blind German speaker, and we have a deaf sign language speaker, and they're both wearing Google Glass, and we're going to have them communicate. So let's see what happens. So the German guy says, "Guten Nachmittag, ich heiße Vint Cerf." Good afternoon, my name is Vint Cerf. Of course, the deaf guy doesn't hear this, but the Google Glass microphone hears that, transliterates that sound into text, and then translates the text into English, and then just presents the English text on the display of the Google Glass so the deaf guy can read what's being said. Now, the deaf guy responds by signing. The blind guy can't see that, but the Google Glass camera sees the signing, translates the signing into English, translates the English into German, and speaks the German using the bone conduction speaker that's on the Google Glass that the blind guy is wearing. So now the two of them are communicating with each other. And ironically, we can actually almost do that. The thing that we don't yet know how to do very well is the signing part, correctly interpreting signs. But that's not completely out of the realm of possibility. So this feels like it's another engineering challenge, but it is not magic. It is simply hard work. And finally, I used to tell jokes about light bulbs having internet addresses. Every light bulb in the theater would have its own IP address. Well, I can't tell that joke anymore because somebody sent me an LED light bulb with an IP address and a radio in it. In fact, Philips makes a light bulb called Hue, and you can not only control the light bulb going off and on, you can change the color of the light bulb remotely from your mobile. So, I mean, this is welcome to the 21st century. Now, the guy in the middle is really something. This is the internet-enabled surfboard. I haven't met him. He's Dutch, I think, and I imagine him sitting on the water waiting for the next wave, thinking, if I had a laptop in my surfboard, I could be surfing the internet while I'm waiting for the next wave. So he put a laptop in the surfboard and put a Wi-Fi service at the Radio Shack, and now he sells this as a product. So if you want to be out there on the water surfing the internet while you're waiting, this is the product for you. Now, I have to say that in addition to the cloud and in addition to mobiles, two technologies that are becoming an integral part of the internet, sensor networks are also a major part of the network. And I have one in my house. It's an IPv6 self-organizing radio network. This is a product. It's not me in the garage with a soldering gun. This is actually something I purchased from a company called Archrock, which was later acquired by Cisco. So there's a dozen of these little sensors. They run on AA batteries for almost a year, and they have IPv6 radios, and they communicate with each other to figure out how the connection works. And then every 5 minutes, each of them samples the light level, humidity, and temperature in each room in the house, and they send that through this self-organized network down to a server down in my basement. So at the end of the year, I actually have engineering data about how well the heating, ventilation, and air conditioning work. And I know that sounds like something only a geek would do, but the point here is that I actually have very good engineering data to figure out how well my HVAC is working and whether or not I should adjust it to work more efficiently. Now, one room in the house is the wine cellar, and that one's alarmed because if the temperature goes above 60 degrees, it's not good for the wine. So if the temperature sensor detects that the temperature has gone up above 60 degrees Fahrenheit, I get an SMS on my mobile. And one day that happened, and I realized nobody was home. We were all on holiday. So I called the Archrock guys, and I said, "Do you have remote actuators?" And they said yes. And I said, "Great, let's get one of those." Do you have strong authentication mechanisms? Because there's a 15-year-old next door and I don't want him messing around with my wine cooling system. They said yes. Okay, so we install that over the weekend. So now when the power goes off or I have to recycle or reset the cooling system, I can do that remotely. But I got to thinking, you know, I can tell if somebody has gone into the wine cellar when I'm not there because I can see that the lights have gone off and on, but I don't know what they did in there. So it's RFID chips to the rescue. I am now going to put RFID chips on every bottle, you know, just hang a little tag on every bottle. And now I can do an instantaneous inventory to see if any bottles have left the wine cellar without my permission. So, you know, I'm boasting of this design to one of my engineering friends, and he looks at me and he says, there's a bug. And I said, what do you mean there's a bug? And he says, well, you could go into the wine cellar and drink the wine and leave the bottle. Oh, several bad words. So now we're going to have to put sensors in the cork. And so as long as we're going to do that, we might as well sample the esters to find out, you know, what is the wine maturing and ready to drink. So before you open the bottle, you interrogate the cork. And if that's the bottle that got up to 90 degrees because of the cooling system failure, that's the bottle that you give to somebody who doesn't know the difference. So this is a very practical thing to have around the house. Honestly, I think these kinds of sensors will be with us everywhere. We will have smart houses, smart offices, smart cars. We will be wearing sensors to what's happening signs. And finally, I think that we'll find this be the first step towards what I'll call smart cities. These are cities that are more aware of the use of resources, of traffic flows and other things that will help the city itself figure out how to configure its own controls to be more friendly to the people living in it. Because this is an example of what we call at Google moonshots. This is a self-driving car. And I want kids to understand that it's possible to do things like this. This is not science fiction. I can tell you that it's a lot harder to get a car to drive door to door than it is to just go on the city streets. Because door to door means you may have to navigate an underground parking garage or navigate to the front door and so on. So it's a big challenge for the Google self-driving car team at Google X. Now I want to spend a couple more minutes on one other topic, and some of you I'm sure have heard about this. The reason I want to bring it up is it's an example of the kind of thing that it's okay to actually think about. I want kids to feel like they're free to roam with ideas in the computing communications world. So this is a project that was started in 1998 with my colleagues at the Jet Propulsion Lab. We had been talking about the planned missions to Mars that were coming in the first and second decades of the 21st century. And we realized that up until the time we were talking about this, all the missions that had been launched used point-to-point radio links for communications, command and control, and getting data back. And that's a pretty thin reed for anything that gets as complex as the number of rovers that we have on Mars now and the number of orbiters. Over time, we anticipated that we would have much more complex configurations of spacecraft in orbit, on the surface, and flying past asteroids and things like that. So we wanted a networking environment comparable to Internet in order to support both manned and robotic missions. So you'll recall that in 1997, the Pathfinder mission landed one of our first successful rovers on Mars. This is the last previous successful one was the Viking mission that landed in 1976. Those were fixed devices. So 97 is Pathfinder. 2004 are two rovers, Spirit and Opportunity, that survived for almost 10 years. The original plan was 90 days. And so this was a mission that had a lifetime way beyond what had been anticipated. The thing that was interesting is that we were beginning our work on network design for interplanetary communication prior to launch of those two rovers. When they landed on the surface, the original plan had been to transmit data directly back from the surface of Mars to the Deep Space Network run by the Jet Propulsion Lab. And what happened is that those radios, which only were delivering 28 kilobits a second for scientific data delivery, overheated. And so immediately, of course, the reaction was we better shut them off or run a lower duty cycle to avoid harming any of the radios that were on board the spacecraft. This was made the scientists pretty unhappy because they were already unhappy at 28 kilobits a second. But then one of the engineers said, you know, we have an X-band radio on the rovers, and we have X-band radios in the orbiters. Now, the orbiters have been sent to map the surface of Mars, and they'd completed that mission. That was to help us figure out where the rovers should go. So both the rovers and the orbiters were reprogrammed to take data from the rover and squirt it up on this X-band radio to an orbiter that was coming around. Now, because they were so much closer than going all the way back to Earth, you could actually transmit the data at 128 kilobits a second. In fact, it's now up to 256. And the orbiter had more solar panels and more power, and it was outside of the atmosphere, so it could transmit back to the deep space net at 128 kilobits a second. 99.99% of all the data coming back from Mars are going through the store and forward network using the prototype software that we were designing for interplanetary communication. I have to say, originally we thought that we could use TCP/IP, you know, it works on Mars, but it would, except that it doesn't work between the planets. And our problem is that the speed of light is too slow. The distance between the planets, when Earth and Mars are closest together, it's 35 million miles. At the speed of light, it takes 3.5 minutes for the signal to get to Mars, and then another 3.5 minutes for something back. And when we're far apart in our orbits, that's 235 million miles. It takes 20 minutes one way, 40 minutes round trip time. Well, TCP was not designed to handle a 40-minute round trip time. Then there's this other problem that's called celestial motion, and the planets are rotating, and we don't know how to stop that. So the problem is that if you're talking to something on the surface and the planet rotates, eventually you can't talk to it until it comes back around again. So it's a very disrupted environment. So we concluded that we had to design what we call delay and disruption tolerant networking protocols, which we have now done. That's what's running in the rovers, that's what's running in the International Space Station, and it's even running on a spacecraft that's in orbit around the sun called EPOXI, which has visited 2 comets in the last decade. We just tested a simulated mission, manned mission, where we had the guys on the International Space Station using the interplanetary protocols, controlling a robot in Germany that was driving around on the surface. So this is to emulate what it would be like if we had astronauts in orbit around Mars controlling directly rovers that are on the surface. So we're really excited about this. It's being standardized through the Consultative Committee on Space Data Systems that standardize communications on an international basis for SpaceCom. And if the spacefaring nations adopt this standard, then all of their spacecraft will be able to communicate with each other, just like we can plug into the internet and talk to 1 billion devices that are on the network. So I'm going to skip through that. So what we're hoping now that the standards are emerging is that we will literally grow an interplanetary backbone mission by mission. So every mission that gets launched, if it adopts these protocols and completes its scientific mission, can become a node in an interplanetary backbone that will grow as the decades go by. But that's not the end of the story. There's a little more to the story. The organization that originally sponsored ARPANET and Internet and sponsored the design of the interplanetary architecture and the interplanetary protocols, the Defense Advanced Research Projects Agency, 2 years ago also funded a research project to design a spacecraft to get to the nearest star in 100 elapsed years. Now, this the nearest star, as you all know, is Alpha Centauri. It's about 4.4 light years away. The current propulsion systems would take 65,000 years to get there. This is a little long even for an ARPA project, since that's 6 times longer than our civilization has existed. So we're going to have to do some work on propulsion. We think that there are some ion engine ideas that could get to 20% the speed of light. And of course, when we get halfway there, 50 years, we're going to flip over and slow down. Otherwise, we'll go zipping through the Alpha Centauri system at 20% the speed of light. We'll get one picture, and that's it. So we need to get into orbit while we get to the other side. Then there's this propagation. You know, when we do interplanetary exploration now, when we send a spacecraft out, somewhere partway through the mission, there'll be mid-course corrections. And, you know, we do that in an interactive way, and we send the signals, the spacecraft fires the rocket for a while, and then it sends back information to help us figure out if it got to the right orbit. Now I want you to imagine if you have a spacecraft that's a light year away, it takes a year to send it a signal and it takes another year to find out what happened. This is not very interactive. So we're going to have to do autonomous navigation in the spacecraft. The good news is that we know something about the proper motion of stars that are in the neighborhood of our solar system, within a few light years. And there are stars that are much farther away in the galaxy that we can use to orient the spacecraft. So we can actually figure out what to do in order to do the navigation towards the destination. And then there's the problem of communication. How do you generate a signal that will actually be detectable from 4 light years away? And so my current thinking about that are femtosecond or attosecond lasers that can compress a 100-watt signal into a really big pulse. 10 to the minus 15th seconds is a very, very short period of time to put a whole lot of energy in. But over a 4 light-year distance, the signal dissipates. It's just like when you hold a flashlight up and you see the beam going like that. Even a laser from 4 light years away is going to have a beam spread that's the size of the solar system. Now you know why I need an interplanetary backbone. I have to build a synthetic aperture receiver that'll reassemble the signals coming from Alpha Centauri. But one of the physicists had suggested one other possibility. If you go 550 astronomical units away from the sun, you will be in the focal plane of the gravity lens. And so if you put the spacecraft in the right place, that's about 55 billion miles away, you may actually be able to reassemble the beam through the gravity lens of the sun in order to detect the signal. So that would be a great test for the ion engines as its initial task. Instead of going to Alpha Centauri as the first test, it can go to the gravity lens and we can verify that the system actually gets there in the appropriate amount of time. So that's the report on the interstellar missions. As for intergalactic, that's somebody else's problem. Anyway, let me thank you for your time, and let me thank you especially for what you do. I hope every one of you is turning on every kid you meet to be a contributor to science, technology, mathematics, and engineering. Thanks very much.
Thank you so much. Really appreciate you coming back.